Hey everyone, and welcome. Today we're going to dive into a really core concept in trigonometry, standard position. Now, it might sound a little intimidating, but honestly, it's just a super simple but powerful way to bring some order to the world of angles.
So let's just jump right in with a basic question. Why all the rules, right? Why can't we just sketch an angle wherever we feel like it on a piece of paper?
Well, the answer really comes down to one word: consistency. Just imagine trying to give directions if your compass pointed one way and my compass pointed another. It'll be total chaos, right? And that's why in trigonometry, we need a universal North Star, a standard agreed-upon way to place every single angle, so we can reliably map them to coordinates and do calculations that work for everyone everywhere. No confusion.
And that's exactly what this system does. It creates order. And believe it or not, it's all built on just two incredibly simple rules that we call standard position.
Okay, so here's the textbook definition you'll see. But what does it really mean? Just think of standard position as the universal starting line for every single angle. It's like a handshake agreement, you know? It makes sure that when I talk about a 45-degree angle and you talk about a 45-degree angle, we are both picturing the exact same thing on the coordinate plane. And this simple agreement, it's the foundation for, well, pretty much everything else in trig.
And seriously, these rules couldn't be any simpler. There are just two of them. First up, the vertex, the corner of the angle, has to be locked right at the origin, point 0, 0. Can't move. And second, the starting arm of our angle, which has a fancy name, the initial side, always lies flat along the positive x-axis. So it's pointing east. That's it. That's our starting line every single time.
So, once that starting line is locked in place, the second arm of the angle, we call that one the terminal side. That's the one that gets to have all the fun. It's free to rotate anywhere it wants. How far it swings open and where it finally lands, that's what tells us the angle's measurement and which of the four quadrants it ends up in.
All right, enough with the rules. Let's actually see this thing in action. Now that we know the setup, we can use it to find any angle's home address on the coordinate plane, which is just another way of saying we can find its quadrant. So here's a classic problem you'll definitely see. If we've got an angle that measures 215 degrees and we draw it in standard position, where is its terminal side going to land?
Finding the answer is actually a super simple check. First, you just have to know your boundaries. Remember, we're always measuring counterclockwise from our starting point. So quadrant I, that's everything from 0 up to 90 degrees. Quadrant 2 takes us from 90 to 180. Quadrant 3 is from 180 to 270, and Quadrant 4 finishes the circle from 270 all the way back to 360. Okay, so that's step 1. Now for step 2. We just compare our angle, 215 degrees, to those boundaries. Well, it's definitely bigger than 180 degrees, but it's not quite 270 yet.
And boom, that puts us squarely in Quadrant 3. See? Simple as that. Once you know those boundaries, you can place any angle, no problem.
Okay, so before we go any further, I want to give you a quick heads up. There is a really common mistake that almost everyone makes when they're first learning this stuff.
Our everyday brains can really trip us up here. We're so used to looking at clocks where the starting point is 12 o'clock, straight up, right? So it feels natural to think that 0 degrees should point north. But, and this is a big but, that's not how it works in trig. As you can see, our starting position is always east along that positive x-axis, and that little shift is absolutely crucial. It means a 90-degree turn doesn't point left, it points straight up to the north.
Okay, so you might be thinking, why? Why do we have to care so much about this one specific starting point? Is this just some random arbitrary rule for a math class? No way. Let's get to the payoff. Because this whole system, this simple agreement, it's not just for a textbook. It is the exact operational logic behind a piece of technology that literally shaped the modern world. Just look at this. A radar system is standard position brought to life. Think about it. The radar dish itself, that's our origin, 0, 0. The direction it starts its sweep from, that's our initial side, pointing east. The sweep itself, that rotation, that's the angle. And when it gets a ping from, say, an airplane, that direction becomes the terminal side, instantly plotting a precise location on a map. It's perfect.
It really makes you wonder, doesn't it? If this simple, elegant system for just placing an angle can guide something as complex and critical as a radar network, what other invisible systems out there in our world, from GPS navigation to video game animation to massive engineering projects, are also secretly being run by these fundamental rules of trigonometry?